So we now actually want to do the most complicated bit of the entire video, which is proving the right-hand rule. So on the picture, we have our vector A here, we have our vector B here, and we want to prove that this answer that we've got here, which we're calling x, is the one that's pointing up like so, the one that obeys the right-hand rule, and that it isn't the one in yellow that is pointing down here, which would directly obey the opposite rule, it would obey the left-hand rule. So we want to show that the orientation of the vectors a, b, and x to one another, where x is this, is the same as the orientation of I, j, and k to one another. We can show that by showing that if we have a linear transformation that transforms I onto the vector A, transforms j onto the vector b, and transforms k onto the vector x, that linear transformation is orientation preserving. And this is the point where we're going to use some advanced linear algebra. In linear algebra, it is true that a linear transformation that is orientation preserving is going to have a matrix with positive determinant. So if we can work out what the matrix for this linear transformation we're planning here is, and we can take its determinant and show that its determinant is always going to be greater than 0, then we have shown that this linear transformation will be orientation preserving, and then that the orientation of a, b, and x to one another is equivalent to this orientation of I, j, and k, which obeys the right-hand rule, and therefore the orientation of a, b, and x to one another will also obey the right-hand rule. So as a matrix, this is what that linear transformation looks like. So we want to transform I onto the vector A, so we need to put the components of the vector A in the first column of the matrix, so A1, A2, A3. We want to transform the vector J onto the vector B, so we need to put the components of the vector B in the second column of the matrix, so B1, B2, B3, and then we want to transform K onto the vector x, so we need to put the components of vector x in the third column of the matrix, x1, x2, x3, where of course x1 is equal to this, x2 is equal to minus what's in this bracket here, and x3 is equal to this. Just to keep it simple, I've just put x1, x2, x3 rather than writing all of this in. So the determinant of this matrix is then going to equal A1 times the determinant of that 2 by 2 matrix, which is B2 x3 minus B3 x2, so that gives this portion here, minus B1 times the determinant of this 2 by 2 matrix here, which is A2 x3 minus x2 A3, so that gives that second bit here, and then it's going to be plus x1 times the determinant of this 2 by 2 matrix, which is A2 B3 minus A3 B2. So expanding this and substituting in the x's gives this here. So let's go through this. So here we're going to get A1 B2 times x3, which is equal to this, which is giving us this thing here. So A1 B2 times, in brackets, A1 B2 minus A2 B1, which is this thing here, x3. Then we're going to get minus A1 B3 times x2, so we've got minus A1 B3 here, and then we want multiplied by x2. x2 is equal to minus this thing, so we've swallowed the minus into the brackets, so it's become B1 A3 minus A1 B3. Then we've got minus B1 A2 x3, so we've got minus B1 A2, and then again we've got x3 here, and then we've got plus B1 A3 times x2 again, which again we want to swallow the negative sign into the brackets, so we're going to get B1 A3 minus A1 B3, and then finally we've got plus x1 times this thing. Now x1 is actually equal to that same thing that you've got in the brackets, so you've actually got A2 B3 minus B2 A3 times A2 B3 minus, and then it's just written the other way around, but again that is B2 A3, so this thing is actually this squared. So expanding this further, we get A1 B2 times A1 B2 gives us A1 squared B2 squared. Multiplying this by this gives us A1 A2 B1 B2 with a minus sign in front of it, so minus A1 A2 B1 B2 here. This one here is going to give us A1 A3 B1 B3, again with a minus sign in front of it. this multiplied by this is obviously going to give us plus a1 squared b3 squared, because the minuses multiplied together will give a plus. Looking at this one here will give us minus a1, a2, b1, b2. Again, I've just rearranged things so that we have the a's at the front and the b's at the back, and then the 1s and 2s in order. Multiplying this by this will give us plus b1 squared, a2 squared. Looking at this one here, b1 a3 times b1 a3 is going to give us b1 squared a3 squared, which is what we've got here. b1 a3 times negative a1 b3 is going to give us minus a1 a3 b1 b3. And then I've just written this final thing as plus a2 b3 minus b2 a3 squared. And then what we're going to do is group these together and show that we've got three things added together that are all squares. So this thing here is going to simplify to this thing here, and again I've used colours to try and demonstrate this. So if you look at this thing that I've underlined in blue here, a1 b2 minus b1 a2, if you expand that, it's going to give a1 squared b2 squared, which is this bit here, plus b1 squared a2 squared, which is this bit here, and then you're going to get minus two lots of the cross term, which is going to be a1 a2 b1 b2, and those two lots of the cross terms is here and here, and you can see that they've both got negative signs in front, so all of what's in blue here can be written as that bit here. Equivalently in green, so if we look at what we've got here, a1 b3 minus b1 a3 all squared, if you expand this, it's going to give a1 squared b3 squared plus b1 squared a3 squared. So here is the a1 squared b3 squared, here is the b1 squared a3 squared, and then you're going to get minus two lots of the cross term, which is a1 a3 b1 b3, which you've got here and here. So all of what's in green here simplifies to what's in green over here, and then finally what we already had here as a square here underlined in yellow, I've just moved over to here. So all of this, the determinant of that matrix up here, has simplified down to this, and what you can see is that it's equal to a square number plus a square number plus a square number. So this is going to be a positive number because it's a square number, this is going to be a positive number because it's a square number, and this is going to be a positive number because it's a square number. Remember, everything here we're dealing with real numbers, so their squares are always going to be positive numbers. So this determinant therefore is going to be positive, and therefore that linear transformation given by this matrix here is going to be an orientation preserving linear transformation, and this is where we're using that advanced knowledge from linear algebra that if a linear transformation is orientation preserving, then the matrix describing that linear transformation is going to have a positive determinant. I'm not going to show that in this video because it would make the video go on for far too long. We'll do another video at some point in the future where we prove that.